So because we're assuming that it's infinitely long, then we can just begin to calculate the distance from both of these things. Now, they tell us that each of these points is 4 centimeters from the intersection. Let's see. And equally distant from both wires. So this has to be equally distant from both wires and the intersection. So from here to here, and then the distance from there and there, that has to be the same. And then this distance over here, from here and down to here, has to be the same. Okay, this drawing is really bad. Yeah, if I was going to draw it again a little bit more accurately, I might say something like, if I take a circle that's like 4 centimeters away from that like this, then the bisector of this line here and the bisector of this, that's where those 2 points are. What's that? Maybe. We'll do the calculations and see. All right, so when I'm going to redraw this so it's a little bit more accurate, you see, like, in order for it to be equidistant from both and along this, I'm going to use this as my radius. So it's going to be like right around here. This would allow it to be the same distance, perpendicular distance from both wires, if it's along that bisector. Does that make sense? Yeah, just the same. That one should be there too. So then this is a 90-degree angle. This angle here is, of course, what? If this is 30, that's got to be 150, right? And then therefore this angle right there must be 75 degrees. Right? And the hypotenuse here is 4 centimeters. Okay, so actually that might be hard to see. Okay, so what I've turned that up a little bit to shaders, this distance, intersection. We've put that 4 centimeters along the bisector of that angle in order to make sure that it's equidistant from both of the other lines. We take the perpendicular distance to those lines, that's got to be the long side of that triangle. And then from that we know that this, based on this right here, because 75, sine of 75 would be d over this. So d is equal to 4 centimeters times the sine of 75 degrees. And what does that give us? Like 3 something, maybe, I guess. 3.86 centimeters, or of course 0.0386 meters. Questions on that one? Now in this area, do you see that both of these fields are pointing out of the board? Because of the yellow field pointing out of the board like that, at that distance. And then over here also pointing out of the field. So they're both, the yellow and the green, are pointing out. And if, of course, if those vectors are both pointing out of the board in the same orientation, parallel to each other, then we can do what with those magnetic field vectors? That we just add them together. And so then, to our equation, B is equal to mu 0 I over, was it 4 pi r? Okay, and then since I is the same, and since r is the same, right, we know it's just going to be 2 times this size. So there's just going to be, B total at that point is going to be, well, there's going to be a 2, and then there's a 4 on the bottom. So that'll just use 0. And then, I don't know, plug that in and get whatever you get. Nice hat.
He's talented.
All right. So the other one, over point, right, is coming out, right? And this was Merlin. Here, this is going in. So these are antagonistic fields. But what we see is the current again is the same. The radius again is the same. But this time we're just going to be subtracting them because they're in the opposite direction. And then I'm guessing that looks like it should be 0. So the question was, wrong in my head, was it?
Yeah. Yeah, the integration will be over 2.
Okay, which will give us pi r. So this should have been 2, excuse me. So I just, sorry.